So I think we should start.
Got you, ma'am.
Yes, sir. Hello, everyone.
Yes.
Welcome to the live session by Professor Geetha Venkataraman in the 2-week refresher course organized by Department of Mathematics and TLC Ramanujan College. Our speaker for the day is Professor Geetha Venkataraman, Dean, Research and Consultancy, School of Liberal Studies, Ambedkar University. She did an BSc in mathematics at St. Stephen's College, University of Delhi, where she stood first. She was awarded an INLAC scholarship to read for the second BA honours, equivalent to masters at the University of Oxford. Her doctoral degree, DPhil, is from the University of Oxford. A Burton Senior Scholarship from Oriel College, University of Oxford, supported her research for the doctorate. Professor Venkataraman's doctoral work was on group theory. She has more than 28 years of teaching and research experience. She's a member of Executive Committee, Indian Women in Mathematics, sponsored by NBHM. She's a member of Editorial Board of Renaissance, a journal of science. She's a reviewer for mathematical reviews of the Mathematical Society, American Mathematical Society. She's a program coordinator for MPhil and PhD program in mathematics at Ambedkar University. She's also the Dean Assessment, Evaluation and Student Progression, Ambedkar University. She's also been a chairperson admissions at Ambedkar University. She has published more than 5 books and 2 chapters in the books. She has given more than 50 talks and conferences and workshops. She had published many papers. We are glad to have you as our esteemed resource person, ma'am. Thanks for joining us. I now request you. Thank you.
Thanks so much, Dipakshi. In fact, I'm glad I was able to have the time to participate as a speaker in the refresher course. Previously, I think when you had a refresher course and had asked me, I was very busy at that point of time. Today, in this, there's a 2-part lecture. There's, the first one will be for 45 minutes, and then we'll take a short break, and I'll come back again. And the idea is that I tell you something about group actions and its applications to group theory. Right. So in the first part, I'm planning to quickly review group actions and the terminology that you will require to move ahead, because some of you may not have been in touch with group theory in the more recent years, and may have done this way back when you were undergraduates and so on. So a quick review, and then the aim in the first lecture is to use group actions to prove Silov's theorems, which is a very nice theorem that we have in group theory, and it is usually done, in the undergraduate, final year undergraduate level, maybe, but often it's not done using the kind of proof that I'm going to talk to you about. So this is a proof that we will do using group actions. And then in the second part of the lecture, the idea is to introduce you to a kind of a group construction, which in a way is very similar to the direct product, but again comes out of group actions and is called a semi-direct product. So the second part of the lecture will largely concentrate on semi-direct products, and once you see what semi-direct products are, you'll realize that many of the groups that you had encountered as examples and so on are all nothing but examples of semi-direct products. So that is what I have for today's session. And since this is being live streamed and I can't really see the participants, in case you have any queries or any doubts, or you want to immediately get that sorted out, then I suggest that you use the chat box, and the organizers are keeping a watch on the chat box. And if there is something that needs to be explained or sorted out, then they will immediately place it to me. They'll ask me that question and I will be able to answer it. So without wasting more time, let me talk to you now about group actions. Okay. So a quick review. Okay. So let G be a group and let X be a non-empty set. We say that G acts on X if there exists a function phi mapping G cross X to X satisfying the following. Okay. And before I write down the conditions, see the image of when I apply phi on this on elements in G cross X, I'm going to use the notation that phi on a G comma X, I will write as G dot X. Okay. And so what are the conditions that need to be satisfied? The first condition, of course, is that for all G in G and for all X in X, we must have the image G dot X is again an element of capital X. The second part, so this is, I mean, kind of ensuring that what we have really is going to be a function. And the second thing is we need to show somehow that the group operation in G and the group action are, they are compatible with each other. So that's essentially what the second and third conditions will say. For every G belonging to G, H belonging to G, and X belonging to X, we must have. So if I apply G to H on X, then this must be the same as multiplying G and H in the group and then applying it on X. Okay. And the third condition that you need is that the identity element of G acts trivially on every element of capital X. Okay, so if these three conditions are satisfied, then we say that G acts on a set X. Okay, and I mean, maybe I should quickly mention something, I mean, a remark. And once I do that, we'll also look at some standard examples. The remark that I want to make here is that if G acts on X, then we have a homomorphism rho mapping G to Sx, which is the set of all permutation. Okay, so I'll just write it as set of all, I mean, or rather I should say group. It's the group of all permutations or bijective functions on X. And what is this homomorphism? So rho will take an element G to the permutation rho G, okay, which belongs to Sx. And how does this permutation work? This permutation means a bijective function on X. So I need to know what it does to any little x in X. So this is nothing but how the image of X under the permutation rho G is nothing but the point of X to which G acting on X takes it to. Okay, so this is for all G in G and for all X in X. Okay. And conversely, so the point is, once you have an action, you're going to get a homomorphism from G into Sx. And in a sense, what you're saying is that every element of G basically permutes the elements of X. Conversely, if there exists rho mapping G to Sx as homomorphism, then G acts on X by G dot X equals, let's look at what rho G does on X. Okay. So this is for you to verify. And of course, I mean, even this you have to verify, right? I'm not proving anything here. I'm just stating this as a fact. So the point I want you to remember, and this is very important, is that G acting on X is the same as saying that elements of G are like permutations of X. Okay, so it's a both way thing that you have. Now let's look at some standard examples. So first I'll start with what are very natural examples. So the most natural example in a way is that if you take G equals Sx and X, of course, which is a non-empty set, then obviously the action of G on X is nothing but the G belongs to capital G, which is the set of all permutations on X. So this is nothing but the image of X under G. And the same thing, if you take G to be Sn and X to be the set 1, 2, up to n, then again, this is the action that we have. So these are all very natural types of action. And you know that another thing that we can do is that if we have X as a non-empty set sitting inside any metric space, okay? Metric space. So for example, X could be an equilateral triangle or a square sitting inside R square. Okay? Then we can talk about G being the group of symmetries of X. This just turns out to be the set of all functions belonging to the permutation group of X, which satisfy an additional condition, which is of distance preserving. Okay, so this is all those rho belonging to Sx, which additionally satisfy the condition that distance between rho x and rho y is always equal to the distance between x and y for all x and y belonging to X. Okay, so this is nothing but, in fact, a subgroup of Sx. Again, this has a very natural action. So this G again acts on X, okay, in the same way as I have described before. Another action which many of you have encountered but probably not thought of it as a group action is, suppose I have a vector space of finite dimension M over a field F. And I take G to be the general linear group of degree M over F. So you can think of it as invertible linear transformations on V, or M cross M invertible matrices over F, whichever you're comfortable with. And again, you have a very natural action of any of this on this vector. So if I think of it as linear transformations, so if I take a T belonging to G and a V belonging to V, then T dot V is nothing but the image of V under the linear transformation. Okay, so these are very, very natural kinds of ways in which you can have groups acting on sets. And now I'm going to give a few examples where groups are acting on themselves in certain ways, or on subgroups, or on cosets. Okay, so the examples are switching a little bit. So one of the actions that I want to talk about is group G acts on itself by left multiplication. Okay, by the way, this group action that I have defined for you is from the left. Okay, you can similarly talk about right group actions and so on as well. Okay, so what is the action here? So G on an X is nothing but the product Gx. For all G belonging to G and X belonging to X, where X is also just G. And see, one thing is, in all these cases, I'm not really proving that these are group actions. Again, I will leave that for you to check. So the next example is G acts on itself by conjugation. Here, the action will be given by G dot X is equal to Gx G inverse for all G and X in G. The seventh example I would like to mention is, suppose I have H, which is a subgroup of G, and I set X to be G by H, or if you want, you can write it G is to H, which is the set of all left cosets of H in G. Right? So this is the set of all GH or XH as X varies over G. Then G acts on this set X again by left multiplication. So how does this work? Take a G in G, take a coset XH, and then the action is nothing but the coset GXH. This is for all G and X in G. And finally, and I'll stop with this, there are many, many more examples, and we'll see some in the course of when I try to prove Sylow's theorems for you. Again, we have the same scenario where H is a subgroup of G, and here I'm going to take capital X to be the set of all conjugates of H. So X varies over G. Okay, so all the conjugates of H in G, and G acts on X as follows. So let me denote this conjugate by H, or doesn't matter, we can write it directly itself. It's not going to really matter very much. G on XH X inverse will just be the new conjugate GX X inverse G inverse. Okay, so that is the action. So, okay, so these are all examples that we have of groups acting on sets. And now let's build up the review a little bit more of the theory. For that, I'm going to set up some definitions. Orbit and stabilizer. Okay, so let's see what these are. So the setting is the same. Let G be a group acting on a set X. See, I'm not writing X as non-empty each time, but I'm assuming it is acting on a non-empty set X. Okay. For each little x in X, we define what is called orbit of X. Okay? And I will denote it by O of X. So this is like, see, the group G is acting on X. So each element of capital G is like picking X and moving it, taking it to another element, which is namely G dot X. So all the possible elements of X, which are of the form G dot X, are called the elements of the orbit of X. So this is nothing but the collection of elements G dot X belonging to X, where as G varies over G. Okay? And so this is clearly a subset of X. The other thing that we will define is called the stabilizer of X. And this I will denote by G little x. And this is the collection of all elements G in G which fix X. Okay. And you can check that this will turn out to be a subgroup of G. Okay. Now, one very important thing which connects O of X and G of X is the following. We have that O of X is in one-to-one correspondence with the set of all left cosets. So this is a 1-1 correspondence. Okay. And why is this the case? So let's see what do elements in the, so I want to basically be able to show that two elements in O of X are the same if and only if their corresponding left cosets are the same. So if I take two elements in O of X, it will look like G1x, G1 dot X and G2 dot X. Now, G1 dot X will be equal to G2 dot X if and only if G1 inverse G2 on X is equal to X. Okay? And this is going to happen if and only if G1 inverse G2 belongs to the stabilizer. And thus, you see that this will happen if and only if the left coset G1 of G1 Gx turns out to be equal to the left coset G2 Gx. Now these two things basically tell you that these two sets will always have the same cardinality. Therefore, what you have, and here I mean this in the cardinality sense, I'm not saying these are finite, but they will have the same size. Of course, if we are dealing with finiteness, if all appropriate are finite, sets are finite, then we get that the order of OX is nothing but the order of G by the number of left cosets of Gx in G, and that that we know by a corollary to Lagrange's theorem is nothing but order of G upon Gx. So this is usually stated for finite groups, so if G is a finite group acting on a set X, which is non-empty, then we have that the order of the orbit of X is equal to order G by order Gx. And this is the fact that they are in one-to-one correspondence is sometimes also called the orbit stabilizer theorem. This is also called the orbit stabilizer theorem. And we will see that this theorem, along with certain other facts, actually gives us a lot of material which we can use relative to our when we want to work with group actions. Okay, now that we have set up orbits and stabilizers, I want to state something further about orbits. So I'll again bring in remarks. And the point is that when a group acts on a set X, you can use it to define an equivalence relation on X. Okay. So we have G acts on X. This is given to us, and we define a relation on X as follows. So if you take for all Y and Z in X, we say that Y is related to Z if there exists G belonging to G such that G dot Y is equal to Z. Or in other words, basically what you want to say is that what you want to say here is that Z and Y, Z is in the orbit of Y. Okay. Right. Now you can verify that this relation is an equivalence relation on capital X, and the orbit, the equivalence class of X under this relation turns out to be nothing but the orbit of X. So what you really have, because of properties that you know of equivalence classes, is that if you think of X as your non-empty set, then you know that it will be partitioned by the distinct equivalence classes. Okay? But the equivalence classes are nothing but these orbits. So you have OY, OU, OV. Or in other words, what we can do is we can write X always as a disjoint union of these orbits where X belongs to X, but we need to put in a condition that, because this indicates disjoint union, that is any two in this union are distinct and they intersect emptily. So what is this condition star? We want only one representative for each orbit. This little x that we are talking about is called the representative. Okay, so this again becomes a very, very important thing in group actions. Okay, so if I call this as a star like this, and I use, so if we have the following situation, so let G be a finite group acting on a finite set X, which is non-empty, then by the orbit stabilizer theorem and above, we get the following, that order of X is nothing but summation order G upon order Gx. I'll just say for some X belonging to X. So this is a big thing that we get. Now, again, as exercise for all of you, what I would like you to do is that find out the orbits and stabilizers for all those examples that I have mentioned earlier, and sort of see what does this this big result tell you in terms of what does it give you? And particularly in the cases where the group is acting on itself, each of these you'll realize is giving you a theorem in that you had learned in your group theory part. So I'm going to call this 1, and I will be utilizing this maybe time and again. And now I want to move very quickly in the time that's left to talk about Silov's subgroups and Silov's theorem. Of course, if I don't finish the proof before, or maybe we can take a break when the proof is over. I don't know how, that depends on the organizers. So let me very quickly take you to a finite group G. This is a group, and it has order p to the power alpha into m, where p is prime and p does not divide this m. So this p to the power alpha is the highest power of p that divides the order of G. So any subgroup P of G with order P equals p to the power alpha is called a Silov P subgroup of G. All right. And so the big question is that, does a group have a Silov P subgroup? Right? We already know, for example, that just because number D is a divisor of the order of a group, doesn't mean that that group will have a subgroup of that order. And the simplest example of this, I mean, the smallest one, is that when we look at A4, the alternating group on 4 letters, we know that it has order 12. 6 divides 12, but A4 does not have any subgroup of order 6. But what Silov's theorem, which we will look at shortly, says is basically every group will have Silov subgroups. That means if I take take A4, which has order 12, then it will have a subgroup of order 4, or it will have a subgroup of order 3, and so on. Right? So basically, if you can write order G as P1 to the power alpha 1 up to P2 to the power alpha k up to Pk to the power alpha k, where the Pi's are distinct primes, then Silov's theorems tell you that you will always have a subgroup in G of order Pi to the power alpha I. So I'm going to first state Silov's theorems, and then we will look at the proofs of Silov's theorems. Yes. So Silov was a mathematician. You can look him up, and you can also, and this theorem is, now quite old. So you can check when Silov's theorems were proved. It says the following, so there is like Silov's theorem 1, 2, and 3. So let G be a group with order G being p to the power alpha into m, where P is prime and P does not divide order G. Sorry, P does not divide M. Then G has a subgroup P of order P to the power alpha. Or in other words, it has a C log P subgroup. Further, if NP denotes the number of C log P subgroups, of G, then we get that NP is congruent to 1 mod. Okay. So this is the first theorem. The second theorem, two C log P subgroups are conjugate, and as a corollary of this fact, you can get that NP has to divide M. And the third thing is that any P subgroup of G is contained in some C log P subgroup of G. Okay, so let me see in the next 10 minutes or so. Let me see if I can prove for you Silov's theorem 1 by group actions. And I really like this proof because it's a very intuitive proof. Okay, so you're trying to produce, so what is given to you? You're given a group G which has order P to the power alpha into M, where P is a prime and P does not divide M. Okay, and you're trying to produce a subgroup in G of this order. Now the point is G will always have subsets of this order, right? We don't have any problem, and we know exactly how many subsets it will have of order P to the power alpha. So what I'm going to do is I'm going to let X be the set of all subsets of G of order P to the power alpha. Okay. Then I know that X is non-empty, and what is the order of X? It is the order of G, P to the power alpha M, and the number of ways in which I can choose P to the power alpha elements out of it. Okay, so that's the order of X. Okay, now what could be the most natural action of G on X? So you have a subset of order P to the power alpha, and so let's see that. So let H belong to X. So what do we know? H is a subset of G. It's not subgroup, and we know it's not necessarily a subgroup, but we know that it has order P to the power alpha, and let G be an element of G. Okay, and I want to define an action. So what should G dot H be? The most obvious thing is to look at the subset G, which I'll denote as G times order H. I mean, the G times capital H, which just consists of all the elements G little x as X varies over capital H. And you can see by the cancellation laws that you have in the group that the order, this will again be a subset of G, and order of GH is the same as order h, which is nothing but p to the power alpha. Okay. So clearly, what we have is that I think my net is a little slow, so just bear with me. I will use this moment to take a sip of water and then get back. Dipakshi, can you hear me?
Yes,
Yes,
ma'am. Yes, ma'am.
Okay, so the thing is that I think my net is a little slow because my screen is not moving.
I think maybe, ma'am, there is some issue with your software, OneNote.
With the OneNote, I mean, it basically is not. You're able to see up to what I have written, right?
Yes,
Up
ma'am.
to the
Everything
p
is
to
the
the power
same.
alpha, ma'am. P to the power alpha. we
Order
can-
GH
Yeah.
is equal to p to the power alpha, you can see. After that, it's not allowing me to move. So I might have to close this and come back again. But what I'm then wondering is, we needed to take a break at 4:15, right?
Yes, ma'am.
So can we take that 15-minute break now and everybody rejoins at 4:25?
Yes, ma'am, because we are just 3 minutes away, so that we can do.
Yeah, and by then my system will reboot and hopefully OneNote will work again, right? So can we all meet back at 4:25 then?
Sure, ma'am.
Yeah.
Sure,
Okay.
ma'am.
Okay. Thank you so much.
Okay.
So I'll come back and join.
Yes, ma'am.
Sure, ma'am. सर लाइव स्ट्रीम बंद करवा दीजिए
नहीं मैम, मत बंद मत करिए
अच्छा
मैम.
चलने दे
हाँ वीरेंद्र सर, फुल वो फोटो वैसे खोल के विंडो शेयर करो सर. हेलो मैम.
Hello.
Hello, ma'am. You are muted, ma'am.
Yeah. Should I share my screen?
Yes, ma'am.
So should I continue or should I wait?
I think you can continue, ma'am.
Okay. So let's come back. Welcome back. And we are now trying to prove Silov's first theorem, which says that let G be a group with order G equals P to the power alpha into M, where P is prime and P does not divide M. Then we have to show that G has a subgroup P of order P to the power alpha. And further, we want to show that the number of Silo P subgroups of G has to be congruent to 1 mod P. And the aim is to do this proof via group actions. And we know that if there's a subgroup, it also has to be a subset. So the idea is that you do know that there are subsets of order P to the power alpha. And so we want to get the group G to act in a nice way on the set of all subsets of G of order P to the power alpha and show via this action that at least one of those subsets has to be a subgroup. Okay, so we note that if you take X to be the set of all subsets of G, which have order P to the power alpha, then obviously X is non-empty and the order of X is P to the power alpha M, choose P to the power alpha. So this notation just means the number of ways in which I can choose P to the power alpha elements out of P to the power alpha into M elements. And how do we define the action of the group G on an element H belonging to X? We know that if H belongs to X, then H is a subset of G and order of H is P to the power alpha. And so we define G dot, what's happening? Just give me a minute. So let's see, has it come back? No. Just give me 1 second. There seems to be some problem with the connection. Let me change. Okay, sorry for this. I think I'm going to have to change my pad. So let me do that. Let's hope.
Ma'am, your internet connection is fine. It must be with the software or pad is not connected properly.
Yeah, the pad is not connecting properly. So I'm just trying another pad. Just give me a minute. This thing has not happened to me before. So the anomalies of, technology.
Yes.
So no, I think the problem is with OneNote then.
So is it you are using this online or this is software installed on your system?
It's on my system. So let me quit it and restart it and
Yes.
then just check. Okay. now I'm going to relaunch my OneNote. Okay, so let me, something is happening. Okay, so maybe it was a question of relaunching. So let me first see if I'm being able to write. Yeah, now it's writing. So it was a question, it probably just hung at that point and then.
Yes.
Yeah, okay. So, yeah, so the action that we wanted to define is, so take a G in G and take an H in X. So this is a subset of order P to the power alpha. And this consists of, what does this new subset consist of? It consists of all the elements of the type G into X as X varies over H. And what you see then is that clearly order of GH is nothing, G dot H is again P to the power alpha and G dot H belongs to X. So this is definitely an action. Okay, now what we're going to do is to try and exploit the orbits and the stabilizers under this action. So let's let OH be any orbit for an H which belongs to X. Now the claim is that, this is my first claim, that OH will have a subset say S such that identity of G belongs to S. Okay. So, and this is fairly obvious to see. If one belongs to H, which is itself a member of OH, then nothing to prove. Otherwise, consider X inverse H, where X is an element of H. Okay, then S, which is equal to X inverse H, is definitely an element of the orbit of H, and 1, which is now X inverse into X, clearly belongs to X inverse dot H, okay, which is our S. Thus, every orbit has a subset containing identity of G. Okay. So let OH1 up to OHK be the distinct orbits and without loss of generality, we assume that the representative HIs, they contain the identity element for all I equals 1 up to K. So please remember the fact that OHI now basically consists of, so for every I, OHI consists of the sets G dot HI where G varies over G. That is your orbit. Okay, so this is a very important thing that we have done. Okay, this was our fact that every orbit has a subset containing identity of G, and we are choosing the a subset which contains identity as the representative, and one we are assuming belongs to HI. Now the second fact about this orbit is that each orbit can contain at most one subgroup. Okay, so what is that telling you? So you look at these k distinct orbits. In each one, either there is a subgroup or you don't have any subgroup at all. That's what is going to happen in each one of these orbits. We'll prove that. But then what is our aim in this whole thing? Our aim in this whole thing is to show that there must be at least one subgroup. And we already know the distinct orbits partition the set X. So basically our aim is to show that at least one of these orbits must contain a subgroup. But for that, the next step that we show is each orbit contains either no subgroups or exactly one subgroup. Okay. Now, so let OHI contain, suppose it contains no subgroup, then we are done. Contain a subgroup, say P. All right. Then by property of orbits, we know that the orbit of HI is exactly the same as the orbit of P. But what is the orbit of P going to be by definition? It is all the left cosets of P in G. Okay. So this is nothing but the set of all left cosets of, P of P in G. Okay. And we know that, so the picture that you have here, this orbit, so this orbit OHI is nothing but all the left cosets. So I have a G1P, then I have a G2P. In fact, I can take G1P to be P itself. Then I have G2P and so on, and some GKP. That is what this orbit looks like. But you know, when you look at left cosets of P, that if this first left coset you've taken as P itself, then none of these are subgroups. These are not subgroups. Okay? Because we know that the distinct left cosets partition, this is not OHI, this is G. Okay, this is G. G is partitioned by the distinct left cosets of P in G, and none of these, all other elements in this orbit will intersect P emptily, therefore. So none of them can actually have identity. So they cannot be subgroups. Okay, so these are not subgroups and are the other elements of the orbit OP, which is nothing but OHI. And indeed, so you're just saying P is the only subgroup which has, and it has the identity element, and the other elements in the orbit actually do not have the identity element. So in fact, what we must have is that this HI is actually P itself. That's what happens. Okay. And nothing else has, none of the other elements are subgroups. Thus, this is the second fact that we have. Thus, for each I, either HI is a subgroup and is the only subgroup of OHI, only subgroup in OHI, or OHI has no subgroups. Okay. So this is what we have as fact number 2. Now, fact number 3 is that we are going to explore the stabilizer. Okay, so what happens to the stabilizer? Let me call it GI, which is GHI, which is the set of all G capital HIs. This is the stabilizer. So this is the set of all G in G, such that when G acts on HI, it just fixes HI. Okay, so this is the set of all G in G, such that the product set G into HI is just equal to HI. And now you know that by fact 1 that 1 belongs to HI. So you can see very clearly that G belongs to GI implies that GHI is HI, which implies that G into 1 belongs to GHI. This is nothing but G. And this we know because it is in the stabilizer is HI. So what we are getting is G belongs to GI implies G belongs to HI. Therefore, for every I, GI is going to be contained in HI. Okay. So let me call this fact as 3. And then we also want to know what happens if HI is a subgroup. Okay. And the next fact is that OHI has exactly one subgroup, HI, if and only if this GI actually turns out to be equal to HI. Okay. This is the 4th fact that we have, and let's just quickly prove this. So in other words, what we are saying is HI is a subgroup of G if and only if GI is equal to HI. Okay. Remember, GI is the stabilizer, so it's already a subgroup. So clearly, if I have to go in the reverse direction, that is, if I'm given GI is equal to HI, obviously HI is a subgroup of G. So I only have to see what happens in the forward direction. Okay, so let HI be a subgroup of G. Okay. Then we know that X belongs to GI if and only if XHI is equal to HI. But now remember, HI is a subgroup of G. So this is asking when is the left coset XHI equal to HI? And we know the answer. This happens if and only if X belongs to HI. Okay. So GI, this is if and only if. So HI, if HI is a subgroup of G, then an element belongs to GI if and only if it belongs to HI. So I end up getting that GI must be equal to HI. Okay. And now we are in a position to actually apply these 3 and 4 mainly. These are the two things that we will use. And what we already know in terms of the result that I proved, that order of X is going to be equal to the sums of the orders of the distinct orbits. Okay. So now we know that order of X is summation I equal to 1 to K order of OHI, because these were the distinct orbits. This in turn is summation I equal to 1 to K order G by order GI. And what are the facts we know? For each I, either GI is equal to HI when, and HI is the only subgroup in OHI, or GI is going to be strictly contained in HI and OHI has no subgroup. Okay, so these are the only two things that can happen. Now, if GI is strictly contained in HI, then order of GI is strictly less than P to the power alpha. Okay. Now look at what the picture is. So we have this X, which we know is partitioned by these orbits OH1, OH2, dot dot dot, OHK minus 1, OHK. And suppose, and we have said NP is the number of CeLO P subgroups of G. Of course, as of now, NP could be 0. We don't know that. I mean, we are trying to show that this can't be the case, but right now we don't know, right? And so let's see what we have. For each orbit, either there is one subgroup or 0 subgroup. Okay. So, and we are taking NP to be the total number of subgroups that are there. So if there are NP subgroups, they have to be distributed in NP different orbits. And in any orbit where there is a subgroup, we know that the GI is equal to HI. Therefore, in this case, order of GI will become P to the power alpha. All right. So come back to the summation. So what is going to happen to this summation? Order G is P to the power alpha into M, and order GI hits the value P to the power alpha every time we have a subgroup. And totally NP of these K can have order P to the power alpha. In all other cases, the order of GI is strictly less than P to the power alpha. So you cannot cancel out P to the power alpha between the numerator and the denominator, right? So there will be a P left over. So what we notice, therefore, is the following. See, therefore, for NP of these orbits, for exactly NP of these orbits, we will have order of OHI is equal to order G by order GI, But these are the ones in which there is a subgroup. So this becomes p to the power alpha into m upon p to the power alpha. So we have order of these np orbits. Each of them must have order m. And for all other orbits, order of OHI is equal to p to the power alpha m upon order GI, which is going to be equal to p times something. Okay, so this is going to be equal to some p times lambda I, as order of GI is strictly less than p to the power alpha. So how many ever p's are there, p powers are there in order GI, not the entire lot will get cancelled. So the net result is that the order of OHI has to have p dividing it. Okay. So let's write this down. So this is congruent to 0 mod p. Okay. Therefore, if I look at this equation, order x is equal to this summation. Using these two facts, and we look at it modulo p, what we'll get is order x is congruent to np times m. So there are np orbits, each of which will have size m. These are the ones with the subgroups. And the rest of the orbits each have order dividing. They have p divides their order. So they're all congruent to 0 mod p. So we get this. Okay. Thus, what we have is p to the power alpha m, choose p to the power alpha, is congruent to np m mod p. This is for all groups. So this is a result that we are getting. Okay, now the problem is, what do I do with this p to the power alpha m, choose p to the power alpha? Okay, you might think that the easiest way is, okay, this is just a number. So let me work it out, open it out and work it out and show that this must be congruent to 1 mod p. But we are actually going to use a trick which makes our life easier. So what we do now is we look at a group which we know exists. And so what we consider is, now consider a cyclic group of order p to the power alpha into m. So for example, say we look at z p to the alpha m. Now we know that for each divisor of a finite cyclic group, it has exactly one subgroup of that order. Okay? So if I take this cyclic group G of order p to the power alpha m, then we know that for G, NP is 1 for this G. In this G, the number of C log P subgroups is exactly 1. Because we know from the theory of cyclic groups that if D divides the order of the group G, then there is a unique subgroup of order D. Thus, if we plug this in this equation, okay, so let me call this 2. Thus, using this in 2, we get that p to the power alpha m, choose p to the power alpha, which is congruent to npm mod p, is nothing but m mod p. Or what we are getting is p to the power alpha m, choose p to the power alpha must be congruent to m mod p. Now again use this in 2 to get that m is congruent to p to the power alpha m, choose p to the power alpha, and this is congruent to npm mod p. So for any group G which has order p to the power alpha into m, if np denotes the number of CeLO p subgroups, then what have we proved? Thus, we have proved that np into m is congruent to m mod p. But m is co-prime to p. But p does not divide m and p is prime. Therefore, we can cancel m. Therefore, np has to be congruent to 1 mod p. But that's it, we are done. So np cannot be 0. Therefore, np cannot be 0. And so we've proved that every group which is of order p to the power alpha into m must have a subgroup of order p to the power alpha. So Celo's theorem 1 is done. Now, if you show that, so for 2 and 3, I don't think if I want to do semi-direct products, I can spend too much time on it. So I'll just very quickly tell you that suppose 2 CeLO subgroups, P subgroups are conjugate. Then you can show that NP is nothing but the order of NP is nothing but the index of Ng of P in G, which is order G by order Ng of P, where P is a CeLO P subgroup of G. So this is the notation. CeL P of G is the set of all CeLO P subgroups of G, and Ng of P, you know, is the normalizer of P in G. Of P in G. Thus, what you get is that NP times order Ng of P equals order G, but Ng of P always contains P. So what you'll have is, this is, therefore you get NP, this has order P to the power alpha into M1 equals P to the power alpha into M. And therefore the P alphas get cancelled and you get that NP divides M. Okay. Now, how do you show? You can actually do the fact that every subgroup of P power order is contained in a CeLO P subgroup, as well as showing that any 2 CeLO P subgroups are conjugate by using the following. Okay, so let H be any P subgroup of G. Okay, so it could also be another CeLO P subgroup. And let P be a CeLO P subgroup of G. What you do is you set X to be the set of all conjugates of P in G. Okay, so X is the set of all GP G inverse as G varies over G, and let H act on X by conjugation. Okay. Using this, you can show that for at least one G, H has to be contained in GPG inverse. And that's it. Then you're done. Okay. So I'm not telling you, it's a similar sort of thing. Look at what's happening to the orbits, look at what is happening to your stabilizers. And from that, you can end up getting that your H, you can work on it and then end up showing that this H has to be contained in one of the conjugates of P. But obviously, if that happens, then you've shown that every P subgroup is contained in a conjugate of P. And in particular, if H is a CELO of Q subgroup, then H and GP, G inverse have the same order. So they have to be equal. And so you get that any two CELO subgroups are also conjugate. Okay, so this so group actions can be used to prove all the relevant, all the CELO sub results. Okay, and now in the amount of time that is left to me, I want to quickly talk about semi-direct products. At least give you an introduction to it and maybe leave some of the actual proofs to you only. Now, before we go into semi-direct products, I want you to recall direct products. Right? So suppose I had two groups, H and N, then you took the Cartesian product of H and N. So it consists of ordered pairs where H belongs to H and N belongs to N. And we could define the external direct product of H and N to be the group with underlying set H cross N and operation given by so if I take two elements in this underlying set H1 N1 into H2 N2, then the product is in the first coordinate do the operation in H, so H1 H2, and in the second coordinate do the operation in the second in N. Okay, and you can show that under this operation H cross N becomes a group and it's called the direct product of H and N. And if you want to look at an internal direct product, we say that G is, group G is an internal direct product of subgroups H and N if one H is normal in G, N is normal in G, and second H intersection N is identity, and third that every element in G can be written as something in H times something in N, and it turns out that this coordinate wise decomposition of an element of G, right? G equals Hn, where H belongs to H and N belongs to N. This is unique. So it's like being able to write G in terms of a coordinate system where the first coordinate is coming from capital H and the second coordinate is coming from capital N. And now what we are going to do is we are actually going to create a new kind of group called the semi-direct product. Okay, I should also mention that, okay, every IDP is isomorphic to an external direct product and vice versa. Okay, you can easily check that. So it doesn't really matter if you study groups, study a direct product internally or externally, it's one and the same. So now I'm going to talk about semi-direct product first internally. Okay. So let me, because that's really easy to look at. Internal semi-direct product. So just look at what we had for an internal direct product. Both the subgroups were normal, they intersected trivially and G was Hn. Okay. Here what we are going to have is let G be a group. We say that G is an internal semi-direct product of well, I want N to be normal, so I should say of N by H if the following happens. First, H is a subgroup of G and N is of course normal in G. So we require only one of the subgroups to be normal. We still require that Hn is 1, the intersection. And the third thing that we do require is that G can be written as Hn. Okay. So basically we are just relaxing one of these things, right? So as an example, if you look at S3, which was the permutations on 3 letters, and I take N to be the cyclic subgroup generated by 1, 2, 3, and H to be the cyclic subgroup generated by 1, 2, then S3 is a semi-direct product of N by H, and the notation that we use for semi-direct product is, so we write H and, sorry, I've got the butterfly notation wrong. So N is the normal part, so it has to go like this. Yes. So N is normal in G. This butterfly thing indicates that N is normal in G and H is a subgroup. Of course, if H also becomes normal, then you'll get a direct product. Okay. So S3 is a semi-direct product. I mean, you can see many different examples. Now, the thing again is that you're going to get this part tells you that every element in G can be written as something in H into something in N. And again, you'll get uniqueness because of the fact that H intersection N is 1. Okay, so note that if G is H1N1 and it is also equal to H2N2, this implies that H2 inverse H1 equals, so I'm pre-multiplying by H2 inverse, and then I will get H2 inverse H1N1 equals N2, and so I have to post multiply by N1 inverse. And this therefore belongs to H. the left hand side belongs to H, the right hand side belongs to N. So both of them belong to H intersection N, which was trivial. And so you will get that. Therefore, H1 is equal to H2 and N1 equals N2. So again, there's a unique way of writing G as coordinates. The first one coming from H and the second one coming from N. But what about the multiplication? Okay, so if I take two elements, say G1, which is H1, N1, and I take a G2, which is H2, N2, then what I see, I want to know how do I multiply these two. And remember, this element has to come back into this form. It has to come back into the form something in H times something in N. So how do we do that? So we have H1, N1 into H2, N2. And somehow I have to take the H2 to the left hand side. But I don't know that N1 and H2 commute with each other. All I know is that capital N is normal in G, and I use this fact. So I can rewrite this as H1, and then I have H2, H2 inverse N1 H2 times N2. Okay. So this is the new coordinate that we are getting. The H coordinate is H1, H2. So there is no change. Remember, in the direct product, H1 and H2 will multiply, N1 and N2 will multiply. But in the semi-direct product, which is not a direct product, what happens is the first coordinate H1 and H2 multiplies as it is, but the second coordinate, you have to twist your N1, you have to conjugate it by H2 inverse and then write it. So this, instead of N1, we have a twisted N1 which multiplies with N2, and that is how the coordinates are working. Okay, now the point is that you will notice that since N is normal in G, you get that H acts on N by conjugation. And in fact, you remember that we get a homomorphism from H into the permutations on N. Here, in fact, you can show that each element of H actually acts as an automorphism of N. It's not just a permutation, it also respects the group operation. And so what you'll get is, therefore, there exists a homomorphism phi mapping H to automorphism of N, where what does phi do? It takes the element little h to an automorphism phi h. And what is the automorphism phi h on any N? It is H n H inverse. Okay. And so coming back to the multiplication, therefore what we have is, we have G1, G2 can be written as H1, H2 into phi H2 inverse on N 1 times N2. Okay, so this is the H coordinate, this is the N coordinate. If you just substitute for H2 inverse N1 H2. All right. So this is what is happening internally, and so you can use this to create external direct product. So if I want to create an external semi-direct product, what are the ingredients? First, H and N are groups such that there exists a homomorphism phi mapping H to, we needed to automorphism of N. Okay. So this gives a special action of, this gives a special action of H on N via phi. So there's a special term for such actions. These are actions which are, they are automorphic actions is what we call them. So if you have a homomorphism phi going from H to aught N, H and N are groups. Okay, then we can create an external semi-direct product of N by H via phi as follows. So we take G, again underlying set is H cross N. This is the underlying set. But now, if I want to multiply two things, H1, N1 into, I'm going to put a phi here because I'm going to use this phi to generate my group. So how do I multiply two things? Just remember what you did here very naturally. So first coordinate just multiplies, but the second coordinate gets twisted. Okay, so H1, H2 will be defined as H1, N1 into H2, N2 will be defined as H1, H2, comma, phi of H2 inverse on N1 into N2. So this is the group operation. And it's an operation. The group part you verify. Verify that G becomes a group under this operation. And it is called the external semi-direct product of N by H with respect to phi, and is denoted usually as H butterfly N. So again, I've got the direction wrong. Sorry. It has to go this way. And a phi is put like this. Okay. And the same thing, G turns out to be the internal semi-direct product of H hat by N hat, where H hat is the collection H comma identity of N. H belongs to H, and N hat is the collection 1 H comma N. N belongs to N, and this is isomorphic to H, and this is isomorphic to N. And another very interesting thing is that H, so if you take the conjugation internally, that will be given by phi. So if I take, if another very important thing is that if you look at H hat, which is H1N, and I take N hat, which is 1H comma N, then H hat, N hat, H hat inverse will turn out to be nothing but 1H comma phi H of N. Okay, so you can check this out. So basically what you get is that every external semi-direct product is also an internal semi-direct product of suitable subgroups. And conversely, you can prove that every internal semi-direct product that you start out with, if you define phi as, this phi of any h is given by the conjugation, then you create the external direct product of n by h using this phi, then your internal semi-direct product will be isomorphic to the external semi-direct product. Since I've run out of time, I'm going to stop here. And so this is just a very quick and brief introduction to semi-direct products. And you get that a semi-direct product is a direct product if and only if this homomorphism phi turns out to be trivial. Okay, and that is the same as saying that internally the elements of H and N commute with each other. And externally, you're basically saying that each element of H acts as the identity automorphism on N. So I'll stop here. So if there are any
Thank you so much.
I can answer, or maybe people can always email me. My email is geetha@aud.ac.in.
Thank you so much, ma'am. We'll now take the question answer session. Rajesh sir, would you please
Yes,
take the questions from the YouTube platform?
Yes, ma'am. So first of all, I would like to thank ma'am for her simple and interesting lecture. So I think it will definitely be useful to all of us in our class lectures. So the first question is, ma'am, one of the participants wants to know some good books on these topics.
Okay, so I think some standard books, of course, there's Dummett and Foote. Okay, let me write it. And Foote, what is it called? I have this problem of either I can remember
Abstract Algebra by Dummett and Foote.
It's called Abstract Algebra.
Yes.
So this will give you a reasonably good introduction to group actions, and I don't think he does the proof of Silo's theorems quite in this way, but you'll find other proofs of not just Silo's theorems, Cauchy's theorem, Cayley's theorem, all the standard big theorems that we've done.
Diagonal groups are also defined. Diagonal groups are also studied properly.
And semi-direct products also you'll find in this, and a discussion on this. So this is because it's abstract algebra and it's dealing with algebra per se, the level will not be too high. Otherwise, you can look at group theory books. But there, then the level might become quite high related to dealing with, semi-direct, even say something like semi-direct products. But still, if people want to look at such books, you can, there's a book by Rotman. It's called Theory of Groups. So this is basically graduate texts in groups, or you can look at Marty Isaac's Theory of Finite Groups. Okay, a book like Gallian, which is Contemporary Abstract Algebra, will also have group actions and so on, but maybe somewhere you'll have to find it. But a traditional book, which is the kind of book that I followed when I was a student, undergrad student, Topics in Algebra by Herstein. he does everything algebraically. He doesn't really go into group actions. And that's in a way a shame, because group actions are kind of the most natural way in which to study groups. So, so these are some of the books that you can look at for topics related to what I've done today.
Okay, ma'am. So next question is that one of the participant is asking for any good research problem in this group action. Research problems, ma'am. Research problems in group actions.
See,
Any good research problem.
Group action is only a tool, right? It's a kind of a standard tool that we use all the time. All right. It's so you will not have a research problem which is from group actions per se, but many of your research problems that you deal with in group theory will be using group actions somewhere or the other in the manner in which you handle it. See, because this, some standard, so representation theory of groups, for example, is looking at special situations where you have a homomorphism from the group G into either permutation groups, or you have a homomorphism from a group G into a general linear group. Okay, and therefore then you're able to study that group either as a subgroup of Sn or Sx, or you're being able to study it in a way as a subgroup of the general linear group, and that allows you a lot of power, because the moment something becomes a subgroup of Sn, you have a natural action of that subgroup on the set 1, 2, 3 up to n. So you can determine many things about that group G by looking at its action on the set 1, 2 up to n. And there are very standard ways in which we study such groups. First, you want to know whether that action of the group G is transitive, which means there's only one orbit, or whether it actually breaks up into orbits. If it is transitive, then there is you go into something called imprimitive and primitive permutation groups. And so these are standard ways in which you study a subgroup of a permutation group. Similarly, if you have a general linear group, then you're getting, and you starting with G as a subgroup of that, then you have a natural action of the group G on the vector space, underlying vector space. And so again, you can study whether there are invariant subspaces in V under the action of G or no. And under certain special circumstances, if the field characteristic is such that it does not divide the order of the group, then you have what is called complete reducibility. So your vector space then splits into a direct sum of invariant G invariant subspaces. So then you know, if that happens, then you can study irreducibility. Then from that, you can go again into primitivity and so on. So group actions is like, I mean, it's the standard method by which you work on many problems in group theory itself. But to ask for a research problem only involving group actions, I don't know.
Okay.
Right?
Okay, ma'am. So there is another question. So one of the participants wants to have some reference to some research work and important open problems involving orbit.
Involving orbits. See, I can't, as I said, orbits is too small a topic in that sense, but I can talk about some open problems in group theory where to some extent you have to use group actions, you have to use representation theory, and you have to use many such things, maybe even combinatorics. Things may come in from number theory, from graph theory, and so on to try and solve those problems. Okay, this is an area of interest that I have. So one simple question that you can ask is, so you can define this function called the enumeration function. And what is it? It's defined from the natural numbers to the natural numbers. And f of n is defined to be the number of groups up to isomorphism of order n. Okay. So for example, if n is prime, then we know that any group of order p is cyclic. So there's only one group. So f of p will be 1 if p is prime. F of p square is 2. Any group of order p square is abelian, and it's either cyclic or it's a direct product of two cyclic groups of order p. If q is another prime, then we know that any group of order pq is either cyclic. So there are some cases where, so if I say p is less than q, and this is 1 if p does not divide q minus 1, and it is 2 if p divides q minus 1. Okay? Now, of course, we are not interested in actual values that happen, but we are in general interested in asymptotic behavior of f of n. Okay, so what happens? What does f of n look like? Can you approximate it by a function involving n, which you understand better as n grows large? Okay, so that's a kind of question that we have. And I mean, f of n, I can tell you that it looks like, you can show that this is always less than or equal to 2 by 27 mu n square plus some error term as n, mu n tends to infinity. And what is mu n? So if n is p1 to the power alpha 1 up to pk to the power alpha k, where this is your prime decomposition, then mu n is the maximum of alpha i's. Okay? So this kind of result exists, but we don't know much about this error term. This is correct. This leading term is correct. But the error term that is there, we have no idea what is the correct value. And when you study group enumerations, you're all the time working with group actions, orbits of different kinds. You're trying to, get some nice actions and so on and so forth to be able to study the group structure of a group which has order n. And one open question that is there is, we don't know if this enumeration function is onto. So if I take the number 1000, is there an n such that the number of groups up to isomorphism of order n is 1000? And the answer is yes. There are some exceptional numbers apart from which every other number has a pre-image, but it's still not solved fully.
Ma'am, one of the participants wants to seek some clarification. So in the last part of proof of Seiler's theorem, you used a trick by assuming that G is cyclic.
Yeah.
But the theorem holds for all groups, not only for cyclic groups.
Exactly. So the trick which is for cyclic groups is only used to try and solve the value for p to the power alpha m, choose p to the power alpha. That's a number which is independent of any group, right? When I talk about p to the power alpha m, choose, so if we go back, See, so, see, when I looked at groups in general, this is what I got, right? So what is this? What does this thing tell you? This thing tells you that you take any group G, which has order P to the power alpha into M, where P is a prime such that P does not divide M, and NP is the number of CeLO P subgroups that it has, then we know that NP into M is congruent to a number on the left hand side. And what is that number? It's the number of ways in which we can choose P to the power alpha elements from P to the power alpha into M elements. Now this part 2 holds for all such groups, right? It holds for any group G which has order P to the power alpha into M, and where NP, of course, I should have said this NP, it's like an NP depending on the group G that I choose. Okay, for different groups G, that NP may be different. Whereas M is fixed, P to the alpha, M, all these are fixed. But this NP thing, it depends on which group I choose. But whichever group I choose, its NP into M will be congruent to this number. So then what I'm doing is, this holds for all groups. So it definitely holds for a cyclic group of order P to the power alpha into M. But in a cyclic group of order P to the power alpha into M, I know that this thing takes the value 1. Okay. So I use that information in 2 and I end up getting that this number on the left, which depends on no group, is congruent to the number M, again, which depends on no group, mod P. So I can plug it back here and get rid of this P to the power alpha M P alpha, because I've now shown that this is always congruent to M mod P. So I end up getting rid of this without actually doing too much work. Right? I'm just using the facts about cyclic groups, which we teach to our second year undergraduates.
Okay, ma'am. So next is that one of the participants wants to know the applications of this abstract algebra in applied mathematics. If there are any.
Lot. Actually, in fact, you can find books which talk about applications of algebra. And there are some very famous one. I'm just forgetting the authors. But so, for example, group theory is used in cryptography. Okay, so your encryption systems that you're dealing with, you can either look at it from, I mean, particularly a very famous one called RSA, which is one of the first implementable public key encryption system that we got. It you can look at it as a result of either elementary number theory or group theory. They're both connected. Okay, so and now there is a lot of work. In fact, that's another area of research that's going on, where people are trying to come up with encryption systems which use some difficult facts about groups. Right? If you know two elements are conjugate in a group, so X and Y are conjugate, but you don't know the G such that Gx, G inverse is Y, you can exploit that to try and create some encryption systems and so on. So encryption is an area where group theory is used and so on. Then coding theory. Coding theory uses linear spaces, right? It uses vector spaces. So that is also part of abstract algebra. I mean, and there's lots and lots. I mean, you know, the best thing to do, I think, Little and Pills. That's the set of authors. It's called Algebra, Applications of Algebra or something like that. That's the book. So if you look that up, it gives you an introductory course in how algebra is applied in a lot of practical things. So I would recommend that. Even your Galleon has applications. Dummett and Foote may not have, but if you look at Gallian, it gives you a lot of places where group theory is used, modular arithmetic is used. It might even, so you'll find that.
Okay. So, ma'am, I want to ask one question that although we can define group actions through normal definitions, like we define vector space or any algebraic or structure, but why we use this function? Because I've seen in many books that they use this function notation, function representation. So, is there any particular importance to that?
See, the point is even your group operation is a function, actually. Right? When we want to talk about group operation, that itself is a function from G cross G to G. But when we study groups, we don't go back to the fact that it is a function. I think, see, the point is when you're doing something like abstract algebra, you're doing group theory, ring theory, vector spaces, we want to start from very basic things and then build up, right? So when you want to do group theory, before you talk about operation, you have to talk about function. Before you talk about function, you have to talk about a relation. Before you come up with relations, you have to talk about set theory. So the typical procession is you do sets, then you know something about Cartesian products of sets, then you can use that to talk about relations, and then via relations, then you move to functions. From functions, you move to operations, and then you talk about semi-groups, and then you come to groups, right? So our entire, because we want to make sure that we are very precise in our language that we use and everybody is very clear about it. So if you go back to the original definition that I gave, why am I saying that it has to be a function from G cross X to X, right? So the point is that the function part is actually giving me the first aspect.
Yes.
Okay, because the function part is
Closure
saying
property.
that for each element in the domain, there is an element in the codomain. Okay, but what is hidden, which I've not said in this, is that G dot X is determined uniquely. So if I have G1 comma X1 equal to G2 comma X2, that is G1 is equal to G2 and X1 is equal to X2, then I want to make sure that the action of G1 on X1 is exactly the same as the action of G2 on X2. And the most obvious way for stating that is through functions. So you want to make sure that when, suppose G has multiple things equal to it and X has multiple things equal to it, if I choose one particular version of G and X, and then I do the group action, I should not get something different when I use a different version, right? Then none of your theory will hold up. Okay, so in order to put down some fundamental truths, we end up using functions. But it's very cumbersome if I have to write phi of G comma X every time.
Yes.
Right? Or even if in a group action, groups, what do? You have star, which is a operation from G cross G to G. But I don't write star of G comma H.
Yes.
Instead, I write G star H.
In fact, we remove the star also.
Then you become G dot H, and then you disappear the dot once people understand that, actually there's an operation between the two elements. So, but we need to set up our basic absolutely right so that we get what we want, right? If we don't set it up properly, then we can, prove anything we like and it won't be actually correct.
Yes. Okay, ma'am. So one last question that I want to ask is, so we know the applicability of group actions in silos and silo theorems, but group actions are considered to be very fundamental in group theory.
Yeah.
So are there any other place where group actions is used in group theory?
So,
prove an important result.
so in many places, group theory is, the theory of groups is developed entirely through group actions. They don't necessarily do it the way we tend to teach it in India, right? For us, the SN becomes an example of a group, right? But if you do something like group actions first, and you do Cayley's theorem, which then tells you that every group is nothing but a group of permutations, and then you study permutation groups in great detail and prove things there, then automatically you're proving things for groups, any group, because every group is a permutation group. Okay, so I mean, in a lot of places, it depends on what approach you want to take towards group theory, but practically any big result in group theory, you can try and think of proving it, approaching it using group actions. And so the theory of group actions, there's not much more than what I have described here. But once you set that up, then for every single example of group action that you have, you'll end up getting a theorem. That order of X. So your class equation, for example, that you do in finite group theory, it just comes out of G acting on itself by conjugation.
Yes, ma'am. We can consider vector space also as an.
Yeah. So in fact, if you want to study the symmetries of a plane, for example, right? And there too, you'll find that the kind of structure that group of symmetries has, you'll immediately get into semi-direct products there. And of course, there's a natural action of the group on the plane. Okay, so which helps you to, look at even specialer kind of subgroups, things which are going to preserve angles between lines, things which are going to preserve congruences. It allows you a richness with which you can develop the theory. So I would, in fact, at one point, when you immerse yourself into group actions, you try to solve any problem using group actions. So the first thing then you think about is, is there some nice way in which I can get the group to act so that the end result of it is what I want to prove. So you get into that kind of setup, and the moment you have a group action, it's really easy. See, for example, if you take a permutation in SN, you can, if I know its disjoint cycle decomposition, I can tell you what its order is. I can say many things about it, right? If I give you an element in an abstract group, can you tell me, even if I know that the group has order some 28 or something like that, all I can say about something about the order of an element is that it will divide 28. Beyond that, I cannot say anything about it. But at the same time, suppose I'm able to, through a group action, take this group into a symmetric group, into some SN, right? Then each element of G is now being seen as an element of SN. And how can I do that? If I can do it, if my group G is going to act on the set 1, 2 up to N in some nice way, and nice enough that it's faithful. So it then goes into as a subgroup of Sn for a suitable N. Then I can say all kinds of things about this G, right? Because Sn has such wonderful structure coming out of how each permutation behaves with respect as a function. That's basically what we are using.
Okay, so thank you, ma'am. And so from the chats, I can see that all the participants have felt that the session was informative, interesting, and helpful, and they all will incorporate all these in their class lectures. So thank you, ma'am.
Thank you so much. Thank you.
So, Dipakshi ma'am, now you can take over.
Can I leave, or you need me to stay a bit more?
Yes, ma'am. Dipakshi ma'am was, I think, finishing this.
Something. Yes, okay.
Thank you so much, ma'am, for an amazing lecture on group and group action. It's always an honor to listen to you. I'm sure participants must be enlightened with your lecture. Thank you so much, ma'am. Thank you for joining us.
Thank you, Dipakshi. My pleasure. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you very much, ma'am.
Thank you, Sumit. Thank you.
Thank you, ma'am.
Thank you. Thanks, everybody.
Thank you.